All right, well, let me first start by thanking the organizers for such a wonderful workshop and conference. It's been a pleasure to be here and see all lively discussions. So I'll be talking about something I've been working on for the last 6 or 7 months or so, which resulted in 2 papers with these 3 people. So Alex is here, Joel Myers at CETA, and Kendrick Smith at Perimeter. So let me start with sort of a bold statement. Maybe it's not that bold, but I think that most things that are linear have been done, at least theoretically. There's some caveats. Of course, we're still going for R in the CMB and modulo Daniel's phase shifts, which I guess are linear, but to some degree, they have been worked out in theory and in perturbation theory, and so in that sense, I think this is not such a crazy statement. And I think also the talks of the last couple days and last 2 weeks while I was here mostly involve nonlinear physics, right? So and these can be categorized in 2 groups, I would say. One discussing early universe inflation, for example, talking about non-Gaussianities. We've seen a lot of talks about that. And at late times, of course, we get nonlinearity for free because of gravity. And so the lowest order in perturbation theory, the first thing you look at is the 3-point function. And so specifically, if there's gravity, you tend to get these recurring correlation functions which couple large-scale modes to small-scale power. Okay, and so as it turns out, if I just go back, this is a blunt advertisement of my own work. If I go back to the stuff that I've been working on, most of the stuff I've been working on the last year or so, they all involve some kind of relation between getting a correlation between a large-scale mode and small-scale power for late-time stuff, and at the same time, when working in inflation, I usually consider non-Gaussianities. So the stuff we'll be talking about today specifically is what I refer to in my talk as Reconstructing CMB fluctuations, and they're aimed at getting the optical depth, and there's a side effect or side project that also shows you can use the same technique to get the intrinsic dipole. So let me start with reconstructing E-modes from having a good measurement of lensing and lensed B-modes. Right, so the problem at hand starts with this attempt of the entire cosmological community to get the sum of the mass of neutrinos. This is something that Mari briefly discussed earlier this week. I think the takeaway point from this figure is to realize to have a guaranteed detection, you need 20 milli-electron volts to get the normal hierarchy. Right? So that's sort of like the ballpark error bar that we need to guarantee detection. And so what do neutrinos do? Well, foremost, they suppress the formation of small-scale structure, and they add to the matter density. And to illustrate that, there's these 2 plots where I show the matter power spectrum for various masses of neutrinos. And again, the takeaway here is that the relative suppression of small-scale structure requires an exquisite measure of the overall power of fluctuations, right? Which is measured by AS or sigma 8. And so how do we usually get to AS? As we all know, we measure, well, first we would measure the temperature power spectrum. Unfortunately, the thing we measure in the intensity is not just AS, it's the primordial amplitude of fluctuations multiplied by the optical depth. And so this is a clear degeneracy. Fortunately, as we know, this degeneracy can in principle be broken when you have large angle E-mode polarization measurements, because they are direct measurement of the optical depth. Right? So here I show the E-mode polarization spectrum as a function of L for very low multiples on large scales for various values of tau. So this is Planck and then the 1 sigma error bar. So you see that this is a direct measurement of tau and could therefore break the degeneracy. Now, the problem at hand is sort of illustrated in this figure, which is that as a function of the temperature noise in your CMB experiment versus the error bar you can get on tau, it's really hard to get to the required level of 20 millielectron volts if you only have observations from the ground, right, with some minimum multiple of 30, for example. This is where Planck is today, and so we can't use Planck to get to this 20 million electron volt, right? So we need to find another way. So what could we do? Well, as Lyman discussed yesterday, we could try and do this directly from the ground. We could build a new satellite. Of course, that would solve everything. But in the meantime, we might want to consider other options, right? Just maybe as a cross-check, for example. So the problem, of course, with doing this from the ground is that you have these, T2P leakage. You can resolve this with these rotating half-wave plates, which is quite magical, as Lyman explained yesterday. And this has already been proven to work to some degree, lowering the minimum multiple from the ground to 50 in the BISEP-CAC experiment. And of course, there is actually an experiment that's going for these very low multiples, which is class, but we'll have to see whether that actually works. For satellites, we have the European effort, which is core. I don't think it has any funds yet. So that's, we'll have to see, and I think even the proposal that I saw last had like a time frame of 2030 or so. Lightbird, I think it's going to fly. I'm not sure who's in charge of that.
Stay until the end of the conference already.
Okay, very good. So this might fly, so then of course we could get there. And Pixie, I guess, is in the same sort of situation as Core. In the meantime, so people have proposed other methods. So there's a group from Berkeley that claim that you can get to the necessary levels in noise to get tau from the 21 centimeter power spectrum at high redshift. So I'm just going to be very agnostic about that. We have never measured 21 centimeter at high redshift, so we'll just have to see if this actually works. But I think we should definitely try. And so in the meantime, we figured this idea using the CMB would be interesting to pursue. And so what is the idea? Well, we know that E modes can be converted into B modes. I mean, we just had like a talk by Alessandro about this. So this happens on all scales to all other scales. The most well-known example is lensing, right? If there's no tensors, then the only B modes that we measure are lensing B modes. And so we know that there exists this correlation which relates the large-scale E modes to small-scale lenses, small-scale B modes, right? And so you can write down an estimator to get back to the large-angle E modes. That was the idea. And we know that this thing exists because this has been measured. In fact, the first measurement of lens B modes was with SVT in some form of cross-correlation. So to get everyone on the same page here, so we have, this is a plot that we've seen a couple of times already, the temperature power spectrum, the E mode power spectrum, the lens B mode power spectrum, the various error bars, and the projected forecast for CMBS4, which is sort of comparable to what XO hopes to do. And then the problem here is that we're stopping here, right, with these experiments. So around L30, well, this is exactly the thing we need to get to this lower bound on the sum of neutrino masses. And so if you write down the unbiased minimal variance quadratic estimator and you compute the noise of such a reconstruction using all modes above L of 30, this is what you get. So again, I show you the E mode power spectrum, and then there's various noise curves. And so for very low noise levels of your CMB experiment, you can actually get below the signal, right, for the actual measurement of tau. And so, but just to show you, sort of as a continuous function of your noise levels, this is a Planck error bar on tau. This is the cosmic variance limit. And as you can see, at some point with this reconstruction, you get below current Planck values. But this is at extremely low noise levels, right? So that's quite unfortunate. In the same plot, we show the tau, the patchy tau effect. So this is much worse, but that's because it's not optimal. So that's another way to get to the low LE modes. Anything that converts E to B can be used, right? So even by effringence. So if we see new physics, we use that. So it could work, So if we, I don't know, somehow never build a satellite again, if we do not trust our class results, then in principle we just have to build a lot of ground-based telescopes to do it. And then of course it doesn't require this detailed modeling of the 21 centimeter field. And of course, because it's a different experiment in some sense, right, using a completely different way to get to the same thing, it has very different systematics. So I think that's kind of a useful feature. You need very low noise levels, unfortunately, beyond CMBS4. So initially the idea was, let's see if we can do this internally with something like CMBS4, so we focused only on the CMB experiment. We didn't include any other external tracers or external data that would allow to improve this. So in principle, the problem is that you're using the lensing potential reconstructed from the CMB, but in principle, you'd be much better off to use lensing potential that's generated around redshift 10, where the B modes are, where the E modes are coming from, right? And then for patchy tau, there's ways forward if you directly measure this on the sky as opposed to some inference from the CMB. I said because as different systematics, you might consider this as a way to cross-check your results, maybe cross-correlate with actual Planck or class results. And then we started thinking, well, this is like kind of a neat idea to get to these large angle modes. Are there any other applications? So of course, the first thing you think about, well, there's this anonymously low quadrupole, there's this dip of L of 30, you can try and reconstruct that. We didn't get too excited about that, so we then thought, well, maybe the one thing you can't measure is the dipole, right? So if there's an intrinsic dipole, you can get to that with this technique. Right, so that's what we did. So this was discussed earlier this week. If there is an intrinsic dipole, say of order the RMS of typical fluctuations, then this would be totally swamped by our kinematic dipole. This is not true if you measure this through this lensing reconstruction technique, because the lensing potential peaks at redshift 2, right? So it has nothing to do with our local motion. So you would directly probe the intrinsic dipole. So it's a little worse because you're not you're actually cosmic variance limited by the scalars as opposed to being cosmic variance limited by the tensors. But you can measure all modes above L equals 1, right? So the idea, again, just in equation form, we try to get this dipole from some kind of convolution of the small scale lenses with a small scale temperature. So this is the result as a function of L max for a cosmic variance limited experiment. There's a bunch of lines, so this is sort of the RMS of your expectation. This is the value of the kinematic dipole. And as you can see here, as you increase L max in your experiment, you quickly become cosmic variance limited if you would be able to do this. We compare this to aberration. So aberration is not a direct measurement of the intrinsic dipole. It's a measurement of the kinematic dipole. But as you measure the total dipole on the sky, you can subtract the aberration to also get the intrinsic one, and it performs much better. In reality, again, we just plot this as a function of the noise level of your CMB experiment, and you do worse because you have to deal with K to Z, right, on small scales in temperature. But again, you still do much better than aberration, and this would already be competitive at CMBS4 noise levels, right? So that's kind of interesting. All right, so what could you do with this? To quote Matt, many subtleties. But I think, at least if you're a theorist, if you have some very clear prediction of what your dipole should be, then of course this could be tested with this technique. It turns out, and this was like a small exercise we did in this paper, that just having this single mode, you can improve the constraints on local non-Gaussian entities by order 10% independent of L max, just because you're correlating this very large mode with small scale modes. In principle, you can constrain supervising Isaac curvature modes, and ... for whatever your theories come up with, I suppose. So the takeaway, I think the linear stuff is mostly done, but of course there's potentially groundbreaking discoveries possible in the CMB coming from traces of nonlinear physics. And I think, for example, lensing is a success story in that case, right? And it's going to improve a lot. When you think about nonlinear stuff from inflation, It turns out to be small just because we have these tight constraints from Planck. But of course, as we've seen in the last couple of days, there might be large interactions in the tensor sector, and so that would lead to large number of Gaussian entities there. So we should definitely try. And at the same time, we should just come up with new observables that are sort of gravity induced that probe new physics, right? So here I showed that there's two examples to get to the neutrino mass, one to get to the intrinsic dipole. They need low noise levels, but I think are still interesting by themselves. So that being said, we still have this issue, right? So we haven't resolved the issue that we were aiming for, getting to tau in any array. And so just to tease you an idea, which is based on work in collaboration with Joel, Alex, and Nick, and also sort of discussed yesterday by Matt, you can use polarized SZ to get rid of cosmic variance, right? And so, for example, let's say you measure the neutrino mass, maybe you want to actually measure the second mass, for example, and then you would be stuck anyways just because of the cosmic variance limited from the CMB. And so here I show you, like, if you measure the electrons out to some high redshift, right, you can actually get sigma, the sigma tau is just, like, there's no limit really, right? So the information in principle is there, and we in principle can probe tau to much lower levels. And I'll leave it at that. Thank you.
Thank you.